In this lecture, we will learn a systematic way of doing circuit analysis. It is called node voltage analysis. After solving complex circuits using node voltage analysis, we will end up with a linear system of equations, which is cumbersome to solve by hand. In order to solve this using a computer, we will learn how to solve these using Matlab. And afterwards, we will conclude this lecture with supernode concept. What is a simple way of doing circuit analysis? We know that the unknown variables are the currents and voltages. We can write Kirchhoff's current and voltage laws to get some of the equations. Then we can generate additional equations using the constitutive relations of different components. For instance, for resistors, we will use Ohm's law. And this method will work quite well for small circuits. But for moderately sized circuits, the number of equations will grow very quickly. For 6 elements, we will have around 12 equations. So in this lecture, we will learn these systematic approaches to solving these circuits, which are node voltage method and mesh current method. We will specifically today cover the node voltage method. Let us first introduce the concept of the reference node. Analyzing a circuit with n connected nodes will require n-1 KCL equations. We will not apply the KCL equation for the reference node. Any node in a circuit can be the reference node. Here, for instance, it is the node C, but it could have been node B or node A as well. However, in circuits with the grounded power supplies, the ground node of the power supply is usually selected as the reference node. Here we see a real-world circuit, most probably a microcontroller, and we observe that lots of different nodes of the circuit is connected to the same reference node, which we also call as the ground. The voltage at any node of the circuit relative to the reference node is called a node voltage. Please remember, we can only define a voltage as a potential between two nodes. But once we start defining the voltages with respect to the reference node, we no longer need to write VAC or VBC. We simply write VA and VB. These mean that the voltages are all referenced to the reference node. The voltage at the reference node then will be 0 volts. In the node voltage method for circuit analysis, we write and solve the node equations. In order to write these node equations, we write element currents as functions of node voltages. For instance, here we have node V1 and here we have node V2. We are writing the current I passing through this resistor as I is equal to V1 minus V2 over R. And in the node voltage analysis, then we apply KCL at each node of the circuit except the reference node. This concept will become more clear when we solve some examples. Let's start with this one. We need to analyze the circuit, and I start by defining my node voltages. Here I have VA and here I have VB. And accordingly, I can define the voltage over this resistor as VA minus VB is here. Now, what do I need to do? I need to write the KCL for node A. What will that be? IS is entering and this current is getting out. So in other words, I can write VA over R2 plus VA minus VB divided by R1 will be equal to IS. Similarly, I can just write the KCL for node B. So the current getting out of here and the current getting out of here, the sum of them will be equal to 0. Let's write VA minus VB divided by R1. So this is the current going this way, this current. And plus VB divided by R3 is equal to 0. Here the unknowns are VA and VB. and we have the rest of the values here. So let's plug in those values and write these equations. VA over R2. R2 is equal to 0.5. 2 VA plus VA minus VB is equal to 4. And for the second one, I have VA minus VB, because R1 is equal to 1 ohm, plus 2 VB is equal to 0. From here, I end up with VB is equal to minus VA. And I can go and plug this into this equation. I end up with 3 VA plus VA is equal to 4. Accordingly, VA is equal to 1 volt and VB will be equal to minus 1 volt. Since I found both of the node voltages, I conclude my circuit analysis. Using these two values, I can find any of the currents. So for instance, let's see what will be the current flowing over R2. So I R2 will be equal to VA over R2, and here it will be 1 volt divided by 0.5 ohms, which is equal to 2 amperes. Okay, in this example, I need to find the value of resistance R, and we can do this by doing node voltage analysis. Let me start by defining my node voltages, VA, and here VB, but I know what the VB is because I have a voltmeter measurement, which is equal to 5 volts. This will be quite helpful for me. Let me try to write the KCL for VA. So this current is getting out, this current is getting out, and this current is getting out. 4 plus VA over 10 plus VA minus VB divided by 5 is equal to 0. Let me simplify this a little bit. 40 plus VA plus 2VA minus 2VB is equal to 0. Now I know VB is equal to 5 volts because the voltage between this node and then the reference node is equal to 5. So then this will be 40 plus 3VA minus 10 is equal to 0, and from here I find V is equal to minus 10 volts. So I know VB and I know VA. So what should I do? Let us try to write the KCL for the node B. VB minus VA divided by 5 minus 4 plus VB over R is equal to 0. However, I know VB, which is 5. I know VA, which is minus 10. So here I will have 15 divided by 5 minus 4 plus 5 over R, which is equal to 0. When I solve this, this will become 3. And I end up with 5 over R is equal to 1. And from here, I find R as 5 ohms. So basically, the value of the resistance is equal to 5 ohms. Now we need to analyze this circuit. This looks rather complicated because the circuit has 1, 2, 3 current sources and 6 resistors. And however, we can analyze this easily using node voltage analysis. Why? Because we have only 3 nodes. One of the nodes is here, another one is here, and the third one is here. So we have 1, 2, and 3 nodes. Therefore, we will need to write 3 KCL equations for these nodes, and then we will just do our node voltage analysis. Now, let's start with writing the KCL for node A. This current is going out by convention. This current is going out by convention. This current is going out by convention. This is entering. And this one is entering as well. So accordingly, we will have VA minus VC divided by R1 plus VA minus VC divided by R2 plus VA minus VB divided by R5 is equal to I1 plus I2. Let us plug in the numbers. We have VA minus VC over R1. VA VC over 5 plus VA minus VC over 2 plus VA minus VB divided by 5 is equal to I1 is 1 and I2 is equal to 2 is equal to 3. So let's continue. 2VA minus 2VC plus 5VA minus 5VC plus 2VA minus 2VB is equal to 30. Now let's calculate 2, 5, and 7. 9VA minus 2VB minus 7VC is equal to 30. This is our first equation. Now let us write the KCL for node B. I2 is getting out, I3 is entering. This current is going out by convention. Again, this one is going out, this one is going out. So I will write this as VB minus VA divided by R5 plus VB minus VC divided by R3 plus VB simply divided by R4 because it's connected to the reference node, and plus I2 is equal to I3. Now let's plug in the numbers. VB minus VA divided by R5 is 5 ohms plus VB minus VC over R3 is 10 plus VB over 4 is 4 plus I2 is equal to 2 and I3 is equal to 3. So this can be simply 1, and let us simplify further. 4VB minus 4VA plus 2VB minus 2VC plus 5VB is equal to 20. Simplify. Minus 4VA plus 11VB minus 2VC will be equal to 20. So this is our second equation, the KCL for node B. And last but not least, let us write the Kirchhoff's current law for node C. So this current is going out, this is going out, this is going out, this I1 is going out, and this current is going out. So let us try to write it. So VC over R6 plus VC minus VB divided by R3 plus VC minus VA divided by R2 plus VC minus VA divided by R1 plus I1 is equal to 0. Let's plug in the numbers. I think I will write this here because I will run out of space. VC divided by 2 plus VC minus VB divided by R3, 10, plus VC minus VA divided by 2 plus VC minus VA divided by R1. R1 is equal to 5 is equal to minus 1. So let us further simplify. 5VC plus VC minus VB plus 5VC minus VA plus 2VC minus 2VA is equal to minus 10. So let's collect these terms. I have minus 7VA. This one is gone, this one is gone. Then I have minus VB, simply. This one is gone. 6VC, 11VC, 13VC plus 13VC is equal to minus 10. If I did not make any mistakes, this is my third equation. The equations for nodes A, B, and C are shown here. It will be not very easy to solve this using paper and pencil. One way to solve it would be using Matlab. In order to do this, we need to first write these equations in matrix form. So I create here my matrix, which will be a 3 by 3 matrix. Here I have a vector of my unknowns. Here they are VA, VB, and VC. And on the right side, I have my constants, 30, 20, and minus 10. Let us populate this matrix A. And this is the vector V, and this is the vector B. So for the first line, I will have the first equation, 9 times VA minus 2 times VB and minus 7 times VC. Similarly, for the second line, I will have the equation for node B, minus 4, 11, and minus 2. And for the third line, I will have minus 7, minus 1, and 13. So how will I solve this? My equation is A times V is equal to B. And I will find the vector of unknowns, which is V, as A inverse times B. We will learn how to do this operation in Matlab shortly. So let me first define the matrix A. A is equal to 9 minus 2 minus 7. I use semicolon to define the next line, minus 4, 11, and minus 2. Next line, minus 7, minus 1, and 13. So A is defined. Now the vector B. Vector V will be 30, 20, and minus 10. Hey, but I defined a horizontal row vector. I need a column vector, so I will define it by taking the transpose. And now I will find the vector V as inverse of A times B. And here I have my results, 7.15 for V1, VA, 5.05 for VB, and 3.47 for VC. An important concept in node voltage analysis is the concept of supernode. A supernode or generalized node consists of two nodes connected by an independent or dependent voltage source. We have two cases. In the first case, the voltage source is between node Q and the reference node. In this case, we set VQ equal to the source voltage, considering the polarities, and write simply the Kirchhoff's current law. In the second case, which is much more common, we have the voltage source between two nodes. For instance, here I have the node A and node B, and I have the voltage source Vs between these two nodes. In this case, we create a supernode that incorporates both nodes A and B and equate the sum of all currents entering to the supernode to 0. You might have noticed that here we are losing one equation and we have missing information to solve the question. That information is coming from this relationship. VA minus VB is equal to Vs. In other words, thanks to the voltage source here, I know the relationship between the node voltage VA and VB, and therefore I write this additional equation and can solve the question. Alright, we need to obtain the node equations for this circuit, and here I see both examples of the supernode concept. Firstly, let's have a look at here. Here I can define VA is equal to, taking into account the polarity of the voltage source, 4 volts. And secondly, I can define a supernode here consisting of nodes B and C, between which there is a independent voltage source, and I can write VB minus VC is equal to 8 volts. In addition to this, I can write the Kirchhoff's current law for the supernode. So this current will be going out, this current will be going out, this current will be going out, and by definition, this current will be entering. So VB minus VA divided by 6 plus VB divided by 12 plus VC divided by 12. On the right side, since these 2 amperes are entering, 2 amperes. Then I can simplify this further. I can write 2VB minus 2VA plus VB plus VC will be equal to 24. And I can write this as equation 1, this is equation 2, and this is equation 3. And I can plug in VA is equal to minus 4 volts to this equation, and I will end up with 3VB plus VC is equal to 2VA is minus 8, so it will be equal to 16. And this will be my fourth equation. Now, if I write the second equation here, I end up with VB minus VC is equal to 8. And if I add these two equations, I end up with 4VB is equal to 24. And from here, I calculate VB as 6 volts. And if I have VB as 6 volts, from equation 2, I will have 6 minus VC is equal to 8. And from here, VC will be equal to minus 2 volts. And I already have VA as well, and I complete the solution of my question. Let's solve this question also using the supernode concept. Here I have VA, and here I have VB, and both nodes A and B constitute a supernode. I can write VB minus VA is equal to 12 volts, taking into account the polarity of the voltage source. And then I will write my Kirchhoff's current law for the supernode. This current will be going out, this is going out, this is going out, and 1.5 amperes is entering. So VA divided by 6 plus VB divided by 3 plus 3.5 will be equal to 1.5. I will simplify this a little bit further. VA plus 2VB will be equal to minus 12. So I have the equation 1, I have the equation 2, and I will write equation 1 here again. Minus VA plus VB is equal to 12. And if I add these, I end up with 3VB is equal to 0. And from here, I find VB is equal to 0 volts. And using equation 1, I can find VA as minus 12 volts. And this concludes my circuit analysis for this circuit. All right, let's obtain the node equations for this circuit. I think I can use the supernode concept here in two places. Firstly, I have this node B, and between this node B and the reference node, we have a voltage supply. So I can simply write VB is equal to minus 12 volts and be done with that. Secondly, I have here node A, and here I have node C, and between node A and C, I have this 10 volt voltage supply. So I can define my supernode as this. It looks ugly, but it follows the definition, and I can therefore do it. This current is going out, this current is going out, this 2 amperes is going out, and 5 amperes is coming in. So let's write these equations. Firstly, let me write the VA minus VC is equal to 10 volts through the supernode, and then write the KCL for the supernode. This will be VA minus VB divided by 10 plus VC minus VB divided by 40 plus 2 is equal to 5 because 2 amperes is going out and 5 amperes is coming in. So let's simplify. Here I have a 3. Then here I can write 4VA minus 4VB plus VC minus VB, I guess. Yes. Minus VB is equal to 120. And I can simply write for VB is equal to minus 12. So I will have 4VA plus 60 plus VC is equal to 120. So this can be further simplified. And I can just go and use the this equation here, this one, and write it underneath this. VA minus VC is equal to 10. So from here I get 5VA is equal to 70 and VA is equal to 14 volts if I did not make a silly grammatical mistake. I know VB here as well, and VC will be equal to 4 volts. Since I know right now the 3 node voltages, I completed the analysis of the circuit. Let us remind us what was the analysis of the circuit mean? Finding all the node voltages using the node voltage method such that I can calculate all the currents of all the elements in the circuit.